Hello everyone. Today our topic is current flow in a conductor. Current flow in a conductor. So in a conductor, electrons are the majority carriers. They flow from one place to the other place. So let us see flow of the electrons in a conductor or the charge carriers in a conductor and all the related terms and the relationships between them. So let us start with this conductor. Here I have shown you a conductor whose length is L. You can see this is the length of the conductor L, and the area of cross section, this is the area of cross section, which is capital A. L is the length, area of cross section is A, and we have given a potential V. We have given a potential V here, and then after that because of the potential which we have given, there is this one electric field is developed within the conductor. That is, E is the electric field. E is the electric field which I have shown here. E is the electric field, and current I flows through the conductor, and electrons being negatively charged particles, they move towards the positive terminal of the battery. You can see this is the direction of the electrons that we call as electronic current, but conventional current direction is opposite to the flow of electrons. Conventional current direction always we show from positive terminal to the negative terminal like this. So these are the notations which we have used here. Now what we have done here is we have applied a battery V with a potential difference V, and current I starts flowing in that in a conductor of length L and a cross sectional area A. So let us start our discussion. Just let us start before applying the electric field. What happens? Before applying the electric field means before applying the battery to the conductor, what happens here? So let us see. What happens is metals means, let us take a metallic conductor of length L and cross sectional area A. They have lot of free electrons. Huge number of free electrons are there. Generally, for 1 cubic meter volume, there will be 10 to the power of 28 electrons are there. So in the absence of electric field, that means when we have not applied any external battery, these electrons will be moving randomly in all directions like this. There is no specific direction for them. Here I am showing they are moving in random directions like this. No specific direction. So if you see, on an average, the number of electrons traveling in one direction is exactly equal to the number of electrons traveling in the opposite direction. So what happens here? The number of electrons traveling in any direction will be equal to the number of electrons traveling in the opposite direction. So what happens? Finally their current, that means the net current in the conductor becomes zero. Why? Because suppose some electrons are traveling from left to right, almost equal number of electrons are traveling from right to left, and then they cancel out each other. So net current will be zero in the conductor. Now let us assume they are traveling, each one of these electrons are traveling with the initial velocities u1, u2, u3, etc. un. Initial velocities or random velocities, and totally we assumed that n electrons are there. Totally n electrons are there. That is our assumption. Then average velocity of the electrons is, take all the velocities u1 plus u2 plus u3 plus u4 etc. un and divide with the number of electrons. that is equal to 0. That is equal to 0. Why? Because on an average, the number of electrons flowing in the one direction and is equal to the number of electrons flowing in the opposite direction. Therefore, net velocity or average velocity is equal to 0. This is equation number 1. Thus, there is no net flow of charge in any direction. Thus, there is no net flow of charge in any direction. This is the point to be noted. This is the case when there is no external electric field. That means it is a simple conductor, no battery is given. Now, the next thing is when we have given the external electric field, that is a battery we have given here. So now once you give the battery or external electric field as shown in the above figure, so electron will experience a force because of the external electric field which is developed because of this applied battery. Then we all know from our first chapter, force and electric field are related. Electric field is equal to force divided by charge. Therefore, force is equal to charge into electric field. This is the relationship which you learned in first chapter. Therefore, these electrons, each one of them have a charge minus E and the electric field is E. So, therefore, they experience a force F is equal to minus small e into capital E, where small e is the charge of the electron and capital E is the electric field. Because electron has negative charge, we are taking it as minus EE. Therefore, we also know another formula, F is equal to ma, that is Newton's second law from the 11th chapter. That means force is equal to mass into acceleration. Therefore, A is equal to F divided by m. Therefore, A is equal to force by mass, that is F by m. But F we have taken as minus EE. Just now we have taken here as minus EE. Substitute the value of F as minus EE. Therefore, A bar, that is acceleration, is equal to minus small e into capital E divided by m, where m is the mass of the electron. Since F is equal to mA, we have done this. And then the next thing is, after applying this electric field, they are moving with the acceleration and they attain some velocities. Each electron, initially they were having the initial velocities like u1, u2, u3, etc. But now their velocities will change. Let us see the reason for the change in the velocity. Because they are accelerated. We have seen the formula for acceleration just now. This is the formula for acceleration. A bar is equal to minus EE by m. This is the acceleration. So with this acceleration, as they are moving, they get different velocities. Why they get different velocities is, they collide with each other, or they may collide with the ions of the metal, other ions of this metal. Then they will be continuously colliding with each other. Lot of collisions will be taking place. Then what happens is, after each collision their velocity keeps on changing. Every time when they collide with other particle, like they may collide with a metallic ion or they may collide with another electron, their velocities change. And then what happens then? The velocity component, they may get another velocity component in addition to its random velocity, that is in a direction opposite to the direction of the electric field. Once again I repeat, between two successive collisions, between one collision and after that another collision, between two successive collisions, these electrons, an electron will gain a velocity component that is in a direction opposite to E bar in addition to its random velocity. Once again I repeat, between two successive collisions, an electron gains a velocity component in addition to its random velocity in a direction opposite to E bar. At each collision, the electron starts afresh with random thermal velocity. After each collision, it starts with new velocity. So that is the meaning of that one. Therefore, let us assume the first electron having a velocity u1, it got accelerated. Let us say it is accelerated, and then the time taken for that is tau 1 before colliding with another ion or electron. Before colliding with another electron or ion, let the time be tau 1. This symbol is tau. It's a Greek letter. It's not a T. We write T like this, but this is tau. T and tau. This is T and this is tau. So this is English letter and this is as Greek letter. And then we use this tau for the time. That is the time taken for this electrons between two successive collisions. We call it as the relaxation time. Later I will tell you what is relaxation time. Then within a time tau 1, it gets a velocity according to our last year, that is 11th standard. V is equal to u plus at. Therefore V1 is equal to u1 plus a bar tau 1. That is for the first electron. Similarly, for the second electron, V2 is equal to u2 plus a bar tau 2, etc., etc. Vn is equal to un plus a bar tau n. So this is about all these equations, that is the final velocities or the velocities attained by the electrons after the collisions. So this is a V. So all together we can put them as equation number 3. Let's take all these things together as equation number 3. I have shown here and also I am writing simultaneously. So in that, with my own handwriting, I have prepared these notes, and at the same time I am writing here. This is the third equation. That is V1 is equal to u1 plus a bar tau 1, etc., etc. Vn is equal to un bar plus a bar into tau n. Next, let us continue. Therefore, average velocity of the n electrons, let us add all these velocities, that is Vd is equal to V1 bar plus V2 bar plus etc., etc., etc. Vn bar totally divided by n, because there are n electrons. So that is Vd, which I have shown as equation number 4 here. You can see here it is equation number 4. So equation 4 is taken as Vd. We call it as the drift velocity. Then substituting equations 3 and 4. Equations 3 means just now I have shown here. This is equation 3. All together I have taken as equation 3. Then substituting 3 and 4. So we can write in place of V1 u1 plus a tau 1. In place of V2 u2 plus a tau 2. And etc., etc. In place of Vn un plus a bar into tau n, and take all u1 u2 plus u3 etc., etc. one side. Take a common out in each of the tau terms, that is time terms, and a bar you have taken out. Tau 1 plus tau 2 plus tau 3 etc., etc. tau n divided by n. So we have separated the terms, that is u1 u2 un we have taken in the beginning, and then after that we have added all of them together and we are dividing with n. We are adding all of them together and dividing with n, and then separately we are taking u1 plus u2 plus u3 etc., etc. un by n plus a bar acceleration common, take it out, tau 1 plus tau 2 plus etc., etc. tau n divided by n. But earlier we have seen this term which I am putting in the bracket. Okay, I'll take another color. This one which I have kept in the blue color, it is equal to 0 from equation 1. I hope you remember equation 1. I'll show you. This is equation 1. u1 plus u2 plus un divided by n is equal to 0. That is equation 1. So we will use that here. That is u1 plus u2 plus un, all this will become 0, and then we will get only the second term, a bar into tau 1 plus tau 2 plus etc tau n by n. Let us take tau 1 plus tau 2 plus tau n etc divided by n as a tau. We have replaced tau 1 plus tau 2 plus etc tau n divided by n is equal to tau. So that is what we have taken. So finally what we are getting here is, we are getting here now Vd, that is drift velocity, is equal to, the first term becomes 0 and the second term is a bar, this a bar, and for all this we have taken as tau, a bar into tau, where tau is equal to tau 1 plus tau 2 plus tau 3 etc tau n divided by n. So let it be equation number 7. So let's proceed further, and if we go further, tau is the average time between two successive collisions. This is called as relaxation time. We are learning another new term. It is the average time between two successive collisions. Then the average time that elapses between two successive collisions of an electron is called relaxation time. The average time between two successive collisions is called as relaxation time. We denote it with tau. That is the Greek letter tau we have used for this relaxation time. This is another term. We have learnt drift velocity. Now we are learning relaxation time. Now let's continue. Then generally this is too small. It is of the order of 10 to the power of minus 14 seconds. That much small. That means 1 divided by 1 0 0 0 0 0 like this, 14 zeros like that we will take, which is a very small amount of time. You know how much small is 1 second, but this is 1 second divided by 10 to the power of 14. Imagine how small it is. It is of the order of 10 to the power of minus 14, and then the velocity gained by an electron during this time, that is Vd, is equal to a bar into tau, just now which we have seen. So this is the one which we have seen. This is the equation 6. Vd bar is equal to 0 plus a bar tau. This formula we are using in the next page. Let's go for that. So this is the one which we are talking, that is Vd bar is equal to a bar into tau from equation 6, but a bar, that is acceleration, is equal to minus E by m, which we have seen earlier. So a bar is equal to, acceleration is equal to minus E by m. In place of a we have substituted this value. Therefore we are getting, that is drift velocity Vd is equal to minus capital E bar tau divided by m. Let it be equation number 8. Now we got the formula for drift velocity. Then coming to the next discussion. So here we got a Vd formula. In general, if the charge carrier has a charge q, so in place of E we will write q. Therefore in place of E we will write Vd is equal to, in place of E we are writing q E tau by m. So this is the formula we are getting in general. Therefore we can say we have to discuss about one more quantity, that is mobility. Mobility is defined as So this is the page where I have explained about mobility. Mobility is another quantity, that is drift velocity per unit electric field. Drift velocity per unit electric field, that is called as the mobility. So before defining mobility directly, I have gone for that equation. So let's come back once again and see this mobility equation once. Drift velocity, it is defined as the average velocity gained by the free electrons of a conductor in the opposite direction of the externally applied electric field. That means applied electric field is in this direction in our picture, but this drift velocity, it is opposite to this one, which I will show with a different color. That's green color. Blue is the color of the electric field, green is the color of the drift velocity, which is in the opposite direction of the externally applied electric field. So electrons are moving with the velocity Vd. So drift velocity, it is defined as the average velocity gained by these free electrons in the conductor. The direction of this drift velocity is opposite to the direction of the externally applied electric field. Then drift velocity for 1 unit electric field, that is called as the mobility. This is mobility. So mobility is defined as the drift velocity acquired by an electron for the unit electric field. So that is, it can be electron or it can be any other charge carrier. Therefore drift velocity can be for any charge carrier. Means when you come to the 14th chapter, that is semiconductors, there you will find two types of charge carriers. One is electron, one type of charge carriers are electrons, other type is holes. So electrons and holes, they move in opposite direction. Generally electrons are negatively charged particles, and we consider the holes as the positively charged particles. They move in opposite direction. So mobility can be defined for any charge carrier. It can be defined for electron or it can be defined for hole also. But in general, mobility is defined as drift velocity per unit electric field. This is the definition of mobility. So let's continue about this mobility. This is equation number 10. Now once again let's come back to this picture, this page. Vd from equation 8, q e tau by m. Vd means drift velocity. That is equation number 8. Here we have defined Vd is equal to Vd bar is equal to minus e tau by m. So this is the equation 8, where we have defined the drift velocity. So let's further proceed, and this drift velocity is, in general, in place of e, we are taking q and e tau by m. Then mu is equal to Vd by e. That means substitute the value of Vd, q e tau by m, and divide with e, then e and e cancel, we will get q into tau by m. This is what we got here, which I have put in the blue color rectangular box, equation number 10. As I told you, two types of charge carriers are there, that is electrons and holes. For electrons it is e tau e by me, and then for holes it is e tau h by mh, because we are putting the subscripts e for electron, h for hole. Then the mobilities of both electrons and holes are positive. Mobilities for both electrons and holes are positive. This is the point to be noted, even though their drift velocities are opposite to each other. Earlier also I told you, electrons and holes, they move in opposite directions. Therefore their velocities are in opposite directions. Even though their velocities are in opposite directions, but mobilities of both electrons and holes are positive only. So with this we can conclude our discussion. What all we have learnt here is, we have learnt the average velocities, that is initial average velocities u1 plus u2, that is etc un by n, that is equal to 0 when we don't apply the external electric field. But when you apply the external electric field, we found the equation for the average velocity, that is called as drift velocity. Then we found the equation for relaxation time, that is tau, relaxation time tau, and also we have found the expression for the mobility, that is mu. So many new terms we are learning. We will come with the derivation in the next video. Next video I will show you the derivations and the relationships between all these quantities. So I hope you understood this topic. We will meet in the next video with new derivations. Until then, bye. God bless you all. Thank you for watching this video.